Okay. So yesterday we were talking about the application of differentiation, all right? I think we left with one last application to cover, and that is the application in economics. So let's go through these few examples to show you how differentiation can be applied to solve some economics problem, all right? Okay, this one we are going to, in this example, we are going to estimate the rate of change, right? Rate of change. And okay, what happened is that there is a company, and you need to spend some money to produce a product, right? And then, of course, it wants to make money, and then, of course, you need to advertise the product, okay? And this table shows the number of years and the corresponding amount of money spent in the advertisement, all right? And we are given that the sales, the annual sale is described by these equations. S, all right? S is the annual sale, so how many units of this product that you can sell, or how much money it can collect from the annual sales. And then this will be in terms of the advertisement, right? Cost, the cost of advertisement X. So of course, if the advertisement goes up, then of course the sale will go up also. So you can see from this equation, all right? So all these are X, and also the sale is in thousands of dollars. So these are spending from year 1 to year 4, and what we want to do is to estimate that in year 4, what is the rate of change of sale, all right? We are not going to get a value of the advertisement cost because it's already provided in the table. Obviously, in year 4, the amount of money spent in advertisement is $20,000, all right? So what we are going to find is in year 4, what is the rate of change of sale, all right? So to do that, of course, the rate of change, meaning that is something is changing with time, all right? So of course, different year, then the annual sale will be different. So from the equation as the annual sale in terms of the advertisement cost X, then to find the rate of change of sale, of course, we just differentiate with respect to time. What we want to get is S prime, differentiation of the annual sale S with respect to time. So to do that, we need to do some differentiation. So based on that, differentiate this, and of course, on the right-hand side, you can see when you differentiate with respect to t, then you need to apply chain rule because we do not know this xt. We do not know the xt. How does x is changing with t, although it is given in the table. All right. So to do that, we need to apply the chain rule. So on the right-hand side, after the differentiation, you see we have an x prime here. So this this comes from the chain rule, right? So this part is actually, okay, this is ds dt, right? Differentiation of s with respect to t. So what we do is we differentiate s with respect to x first, according to chain rule, right? So ds dt is, okay, so ds dt, according to chain rule, we differentiate with respect to x and then multiply to dx dt, okay? So dx dt, you get x prime, ds dx, you just differentiate this function with this function differentiate with respect to x, you will get this part. So I think I leave it to you to go through the differentiation. So this is how we obtain s prime. And of course, to obtain the rate of change of sale, s prime, one need to know xt as well as x prime t, okay? So XT is, of course, the cost of advertisement, and we are looking at year 4. So XT, the advertisement cost is $20,000. So XT is 20, as you can see here. Yeah. In year 4, the cost of advertisement is 20,000. So this will be 20, and then X prime T is the rate of change of the advertisement cost in year 4. Now this one we can estimate from the table. So if you look at the table, year 1, 14.5, year 2, 16, year 3, 18, increase of 2, right? Except from year 1 to year 2, there's an increase of 1.5 thousand in advertisement cost. But from year 2 to year 3, the increase is 2,000 for that year. From year 3 to year 4, also 2,000. So maybe what we can say is, in year 4, the rate of change of advertisement cost is just 2,000 per year, right? Per year. From year 3 to year 4, you see there's an increase of 2,000 per year. From year 2 to year 3, also the same. So we just say, in year 4, we say this is 2,000 per year, all right? That is the rate of amount of advertisement cost in year 4. So with this number, X prime equal to 2, X equal to 20, you substitute inside, then that will give you S prime T. You can calculate the value, turn out to be 0.768. So this means the sale in the 4th year is 760. That means $0.768 thousand, which means $768 per year. All right. So I think it just show you a very simple application of differentiation. And of course, we have a few more examples, 2 more examples in economics. And now, so those of you who have learned economics before may recall what we mean by marginal cost and marginal profit. All right. I never done economics in my life. I mean, just think about it. I don't think so. I never done economics in my life. Yeah, I never chose this subject in my study. Anyway, what it says is pretty clear here. So marginal cost is actually the cost of producing 1 unit of good, right? Let's say in a production. Okay, so that is called the marginal cost, and then it's defined to be the derivative of the cost function. Okay. So that means so long as we have the cost function, we just differentiate it, then we get the marginal cost, so which is the cost to produce 1 more unit of the product. And marginal profit, again, is defined in the same way. It's just that the cost, of course, profit will be for sale, right? So this will be the cost of selling 1 additional unit of the product, okay? And that is also the derivative of the product function. So derivative of the cost function will give you the marginal cost, whereas the derivative of the profit function will give you what is defined as marginal profit. So let's look at this example. So we are given the cost function. So C is the cost function, which is in terms of X. X is the number of units produced. So that can be called the product level. Yeah. How many product is produced. So this cost function will give you the total cost, and the unit is in dollar, right? To produce X units of a product. So if the company produce 100 units, then X will be 100, and from this equation, one can obtain what's the cost of producing the 100 units, right? So that's the cost function. And what we want to do is to calculate the marginal cost at X equal to 100. That means the number 100 product. Okay, the company produce 1 unit, 2 unit, 3 unit, and so on. When it comes to 100, then what is the marginal cost? So that's what we are looking for, and we are also asked to compare this with the actual production cost for the 100th unit. So that's what we are going to do. And of course, just now, the marginal cost is defined to be the derivative of the cost function. And the cost function is given already. So this is a cost function. So we just have to differentiate, all right? So differentiate this. So this is a cost function given to us. And then differentiate is a simple thing to do, 0.04x plus 2, all right? And since we are looking at the marginal cost when X equal to 100, that means for the 100th product, number 100, all right? Then the cost to produce this 100th product will be like that. So you just substitute X equal to 100 there. So that will give you 4 plus 2. So that means to produce the 100th product, the company needs to spend $6 on it. And of course, the cost to produce the product will depend on whether you are looking at 100th product or whether you are looking at the first product. Yeah? Of course, why is that so? I believe this is when the number of the product goes up, then the cost will go down, because when the company produces more and more, of course it will be cheaper to produce, right? Mass production. Producing a 1,000 unit is much cheaper than producing, let's say, 100 units, isn't it? Yeah. Because due to mass production, a lot of costs can be saved. For example, starting costs, buying of equipment, maintenance, manpower costs, all those will go down if the product level goes up. Yeah. So maybe if you have done economics, you can teach me also, because I told you already, I never learned economics in my life. So that is the marginal cost. All right. So now let's work out the actual cost. Yeah. Of course, the actual cost we can work out from the cost function, right? So if the company produce 100 products, then X will be 100. You put X equal to 100 into the cost function, you get the total cost to produce 100 units. And then if we subtract the cost to produce 99 units, then this will be the actual cost to produce the 100th unit, isn't it? So we take C100 minus C99. So this part is the total cost, the actual cost to produce 100 units. This part is the actual cost to produce 99 units. So you take a subtraction, you get $5.98. So somewhat slightly less than $6. So the marginal cost is higher than the actual cost. I think the reason is because marginal cost will take into account of all the various costs involved, things like setup costs, manpower costs, equipment costs, and all this is included in the marginal cost, if I'm right. But if I'm wrong and you have done economics before, please correct me afterwards. And the actual cost doesn't take into account because you take the subtract. You see, of course, the production cost for 100 units will take into account of all the startup costs and so on. And then since you subtract away this is going to be subtract away from the production cost for 99 units. So all these startup costs and all these are not actually counted, and therefore it ends up with a somewhat cheaper, the actual cost. If let's say all these various costs are not included, obviously it's going to be cheaper, isn't it? So I guess this will be the explanation why the actual cost is cheaper than the marginal cost. Okay? I hope this is correct. Let me know if I'm wrong. All right, another thing in economics also quite important is the average cost to produce a product. And that will, by definition, that is the production cost, CX divided by the number of units produced. So that is the average cost, okay? And we have a C bar to denote. And in this example, what we want to do is to find, again, we are given the cost function, CX, all right, the total cost. And we want to we want to minimize the average cost. So how many products should the company produce in order to minimize the average cost? So I think if the production level is too low, obviously the cost will be high because all the startup costs, equipment, and all this will be expensive, isn't it? The company needs to buy equipment, set up the space, find a space and all this. So the production cost, when the production level is low, obviously the production cost will be high. On the other hand, when the production level is high, is too high, let's say, then doesn't mean the production cost will be low, I think there may be some maintenance costs involved, right? Maybe some breakdown of equipment the company need to replace from time to time and all this. So that will increase the cost. I mean, so on one hand, the higher the production level, then of course, on one hand, the cost will go down because, you know, the place to get a venue and the startup cost, a lot of costs will go down. But on the other hand, there will be some cost component which goes up, things like maintenance costs, equipment replacement, and all those will be costly if the production level is too high. So what we're going to do is to minimize find what should be the production level in order to minimize the average cost, all right? So I think that explains why there's a minimum, all right? Too low, the production level too low, no good. Too high may not be good also. So it depends on the cost function. So based on the cost function, we divide by x, and according to definition, that is the average cost, C bar. And then apply differentiation. What we want is to minimize the average cost, right? We are going to minimize this C bar. So it will become a maximum and minimum problem that we went through in detail yesterday. So differentiate this. Maybe I should switch off the light. How to switch off this light? Just give me a second. I think the light is too bright. Never mind, I cannot find the switch. I try to find it later on. Yeah. Are you okay? Can you see? Okay, I can see. All right. Cannot see you? Please raise your hand. Maybe it's too bright for you. Okay. So based on the C bar, then the average cost we just differentiate, and of course we can. That means we want to find a critical point, isn't it? This is a maximum and minimum problem. So we want to find a critical point. We must equate C prime to 0. That was discussed in detail yesterday. So equate C bar prime to 0. Then we can solve for the production level X. How many units is going to be produced correspond to this critical point or critical number. And so you solve this one, you find X equal to plus minus 447. Okay. Of course, this one. You have two roots, so you solve this. And then obviously the production level cannot be negative, right? The company is producing, right? So we have to drop the minus sign. Therefore, we take 447 to be the critical point. Yeah, 447. Negative number is dropped because production level cannot be negative. Okay, now so now this production level, does it correspond to maximum average cost or minimum average cost? We want to minimize the average cost, isn't it? So now we've got to look at whether this is represent a maximum C bar or minimum C bar. So to do that, we can apply the two tests, either the first derivative test or the second derivative test, what I talked about yesterday, right? So in this case, the first derivative test is used. So if you look at that, when X is less than 447, then you can see that C bar prime is negative. So that means when X is less than 447, below this level, then the function C bar is actually decreasing. That is the first derivative test we talked about yesterday, right? On the other hand, when X is bigger than 447, then from this C bar prime, it shows this is positive. So meaning that the C bar, the average cost, actually is increasing. Yeah. So if it is less than 447, decreasing, the C bar is decreasing. Bigger than 447, this is increasing. So obviously, it's a concave up. Yeah. So this corresponds to concave up. and therefore it means we have a minimum. All right. So at this level, when the company produces 447 units, then the average cost will be the minimum. All right. So I think, although the problem is quite simple, but practically it's very useful. It helps the company to determine, how many products to produce in order to bring down the average cost, and that will be that. On one hand, on the other hand, that will determine, how much money, how to price the product when a company wants to sell it. Right? So these are very useful applications, and of course, okay, this one, I think this chapter we finished already, but there are many other applications relating to differentiation. So what I can cover for you are those few until this economics. There are many others, okay, in science and engineering. Even in the stock market, people have been trying to model the stock market movement, and that will involve a lot of things, including differentiation as well. So differentiation has many applications, actually. All right. So I hope you can appreciate there are a wide variety of applications which are quite important, for this differentiation. That's the reason why I spend most of the time in this topic, differentiation, and also the next topic, which are equally important, and that is integration. All right, differentiation and integration. Okay. Okay, the next one will be integration. All right, so let's start the new topic on integration. We start from scratch so that you know the development of the integration and the techniques of integration and so on. So what I'm going to do today is talk about the indefinite and definite integral. All right, antiderivative is related to indefinite integral, and of course I will talk about definite integral, and then the very important fundamental theorem of calculus. Without these, we are in trouble. There are many integrations we can't evaluate. So this fundamental theorem of calculus is very useful. It is very simple, but yet very useful. When we do integration, we almost always rely on this fundamental theorem to do the integration, actually. And then, of course, I will talk about the different techniques of integration. The first one is the substitution technique. And then the last one I talk about, hopefully today I can also cover numerical integration. All right. 4.8, let's drop it. 4.8 is not there. I forgot to just cross it out. This is not inside the notes. This part, 4.8, is not inside the notes. All right? So this is what I'm going to cover in integration. And of course, after that, I will talk about more integration technique after this chapter, and also application of integration. All right? So we're going to spend maybe at least 2 sessions on integration. Yeah? Okay. Let's start with what we call antiderivative. All right, antiderivative. The word implies that it's just the opposite of derivative. Well, you can consider that to be some kind of integration, but normally we call it antiderivative. All right. So this antiderivative is the opposite of differentiation, and therefore it is a way to undo differentiation. You can consider that to be some kind of inverse or something like that. But I think it would be easier if you think of it being a technique to undo differentiation, just like plus minus times dy, and so on. Yeah, there are many things in mathematics which undo each other. Okay, so what we mean by undo differentiation? Let's say, supposing we are given a function, right? We are given a function fx, okay? Then the capital Fx is what we define to be the antiderivative of f. That means we want to find a function for which we differentiate, we are able to obtain the given function small fx. Yeah? So given a giving a function small fx here, then what we're going to do is to find the capital Fx, which you differentiate to produce the given function fx. Okay, so that is called the antiderivative of f. Now maybe we look at a simple example. All right, so after I mean, this is a definition of antiderivative. So what do we mean by that? Maybe this example will give you a better understanding of what we mean by antiderivative, all right? So we are given a function fx, which is x squared. To find the antiderivative, that means we want to find a function which, after differentiation, will produce x squared. So the answer is very simple, because this function is very simple, x squared. So what integrates to produce x squared? I think by inspection you can see it's just 1/3 of x cubed. You see, you differentiate 1/3 x cubed, you get x squared. That is something very simple. One can obtain by inspection, right? And of course, this comes from the power law for differentiation, right? You differentiate 1/3 x cubed, you get x squared. So is 1/3 x cubed the only antiderivative for this given function x squared? The answer is no. There are many, many others. For example, 1/3 x cubed plus a constant is also another antiderivative of the same function x squared. The reason is because when you differentiate 1/3 x cubed plus a constant c, you still get the same function x squared as given by the question, isn't it? So no matter what this constant c is, when we differentiate, well, this part has to be 1/3 x cubed, but this constant can be an arbitrary. No matter what the value of c is, then this will give you x squared after differentiation, isn't it? Therefore, for this given function, there are many, many antiderivatives depending on the constant c. All right? So we have a family of antiderivative for a given function. And this graph, this diagram shows the family of the antiderivative for x squared. All right? Now, each curve correspond to a different value of c. But all of them conform to this function, 1/3 x cubed plus c. Okay? For example, let's say this one. This one. This one, of course, corresponds to c equals 0. C equals 0, this curve, the blue curve going through the origin is actually 1/3 x cubed. Yeah? I mean, elsewhere, this one corresponds to c equal to 1. And then this one, the other one, this one corresponds to c equal to 2. This one, c equal to 3. The other one, this one, c equal to -1, and so on. So you see these are a whole family of antiderivative for the same function. They all antiderivative, all right? But the elementary one is this one, c equals 0. If you put c equals 0, we get what we call an elementary antiderivative, the basic one, you can call it, yeah? All right? Okay, that is what we mean by antiderivative. So this example shows that given a function, let's say if you have an antiderivative fx, then fx plus c is also antiderivative. So the constant, this arbitrary constant, it doesn't really matter, all right? Now, this concept will bring us to the indefinite integral, okay? So since fx plus c is the antiderivative of the function small fx, then we define the indefinite integral of fx to be the antiderivatives, fx plus c. Of course, c is an arbitrary constant. You have seen it, right? Okay? So this is the concept. This is what we mean by indefinite integral, okay? So we just integrate something, then we get what we call the antiderivative of fx, all right? All right, and of course, there is an arbitrary constant. This is often called the integration constant, rather than arbitrary constant, although it is arbitrary. It is due to the integration, and therefore, usually is called integration constant, okay? So that's indefinite integral. So if you want to integrate something, then you just have to find the antiderivative of this fx. And then you add a constant c, that will be the answer. All right? Now, in this definition of definite integral, there are a few terminology. First of all, the process of doing the integration. You want to integrate a given function, and the result is the antiderivatives. Then this process is called integration. All right? And within this antiderivative, The fx inside here, this part, is called the integrand. Integrand, yeah? So this one, integrand. So integrand. This one. All right? And this x, we are integrating fx with respect to x, and this x is called the variable of integration, this one, yeah? So the variable of integration is this. What are you integrating with respect to? So that variable is called variable of integration, okay? All right, so just some terminology. Now we can start working out some example already. So just bear in mind, when you integrate something, we are actually looking at the antiderivative. What, after differentiating, will produce the integrand? And that is the antiderivative, all right? Okay, this example, we want to integrate t to the power 5. So to do that, well, I think this one, again, is something very simple. By inspection, according to power law for differentiation, one can see that when you differentiate t to the power 6, you get 6t to the power 5, isn't it? So if we divide by 6, divide both sides by 6, so this, in other words, this 6 move to the left-hand side. I mean, you can see from here also. If you differentiate 1/6 of t to the power 6, then you get exactly t to the power 5, which is the integrand. Therefore, this is the elementary antiderivative of t to the power 5, right? So 1/6 times t to the power 6 is the elementary antiderivative of the integrand, which is t to the power 5. And therefore, the result of this indefinite integral will be the elementary antiderivative plus an arbitrary constant. Now you know where the arbitrary constant comes from, right? Because when you differentiate constant, you get nothing. So that's why when we integrate, we always get an arbitrary constant, isn't it? Okay? Now, but of course, this one is very simple, t to the power 5. So by inspection, we can see what is the antiderivative. But what if the integrand is more complicated? We can't see from inspection, isn't it? This one we can see by inspection. But if the integrand is getting more complicated, then we are into trouble. So we are going to develop a lot of rules for differentiation, which we can use. Practically, we don't use inspection. I mean, of course, it failed. I mean, inspection for simple problem, if the integrand is very simple, then you can see what is the antiderivative. But if the integrand is somewhat more complicated, then we can't see it, right? So we have to find a way of working out the antiderivative, all right? So I'm going to show you a lot of rules for integration, okay? Now, first of all, every differentiation rule will give you one integration rule. Just now you have seen, this is a power law in differentiation. And the power law in differentiation will give you one rule. You integrate this one, you know what to do already. I mean, okay, this one is the use of power law, right? So you can see that using the power law, when you differentiate this, x to the power r plus 1, r is a constant, all right? R is a constant, but it's not a fixed constant. It can be 1, can be 2, can be 3, whatever. So it's just a constant, all right? So you differentiate this x to the power r plus 1 over r plus 1. According to power law, for differentiation, we get x to the power r. And this will give you one rule for integration. Because from there, you know that when you are integrating x to the power r, you are looking for the antiderivative of x to the power r. And that would be this part, because when you differentiate this, you get x to the power r. So this simple power law for differentiation will give you one rule for integration. And every rule, every differentiation rule will give you one integration rule. Okay? So this is only one of the many integration rules that I will be talking about. So from there, from this power law in differentiation, one can write down this, our first rule for differentiation. When we integrate x to the power r, the antiderivative is this x to the power r plus 1 over r plus 1. And therefore, the answer for this integration is the elementary antiderivative plus a constant. So this is the first rule. So whenever you integrate something like that, x to the power r is a constant, then straight away you can write down, according to this rule, you can write down the result already. Yeah? You don't have to use inspection anymore. Just apply this rule, no matter what the constant r is. All right? So let's look at this example. Of course, this simple one can obtain by inspection also. But we are going to use this also known as the power rule for integration. We have a power rule for differentiation, but this one is the power rule for integration. So the first one, x to the power 17, to integrate according to the power rule, whatever the exponent is 17, right? Whatever exponent, here we have to add 1 to the exponent and then divide it by the exponent, isn't it? And then add a constant c. So that's what we do. So that is 17 plus 1 for the exponent, and then divided by the same number, 17 plus 1, and then we add a constant c, arbitrary constant or integration constant. So that one you get the answer. Okay, very simple power rule. And this one, okay, this one we can change it to exponential form. This is an exponential function, right? X to the power minus 3. So this is a base, this is the exponent. Remember when I talk about exponential function? Yeah, the base, and then this is called the exponent. So it fit into the rule, to this power rule. X to any power, then we can apply this power rule for integration. So what we do is same thing. So it's the same variable x to the power minus 3, we add 1 to it, and then divide by the same number, we add a constant c. So that will give you the answer, right? So very simple. Then if we have a fractional exponent, so let's say these two cases, the first one, square root of x is x to the power half. So the exponent is half, which is a fraction. So no difference at all. We just apply the power rule for the integration as usual. So whatever exponent, we just add 1 to it. So it will be half plus 1, right? And then divided by the same number, half plus 1, and we add a constant c. And you simplify this, you get the answer. If it's 1 over the cube root of x, same thing. We change it to exponential form. So this is the same as x to the power minus 1/3. And then we can apply the power rule. So minus 1/3, we just add 1 to it, yeah? And divide by the same number. And then we add a constant c. So pretty straightforward for this power rule. So there are many other rules for integration. I mean, if you look into the mathematical handbook, which contain extensive list of integration rules. There are many pages for integration rules, you know. So I can only give you the standard one. If you look into the mathematical handbook of formula, handbook of mathematical formula, things like that, then they give you a very long list of this integration rule. Just bear in mind, every differentiation rule will give you one integration rule. The first one we have seen. So this one is the power rule we have seen. Second one, the integration of sine x dx is minus cosine x plus a constant. This comes from the differentiation rule because we know from differentiation, all of you have learned that differentiation of cosine will give you minus sine x. And of course, this minus, we can bring it to the left-hand side, right? Or this minus, we can actually put it inside. So this is a differentiation rule. If you differentiate minus cosine with respect to x, you get sine. So from this rule, it means the antiderivative of sine x is actually minus cosine x, and therefore we can set up the rule. So all these parts are the so-called antiderivative. This one, yeah? So these parts are all the antiderivative of the integrand. So the antiderivative of sine x is minus cosine x, as you can see from the differentiation rule, and therefore we can set up this integration rule. So we do this for all the rest, right? So integration of cosine, you get sine x plus c. That also come from differentiation rule. All the rest come from differentiation rule. There are a lot more than this. Okay, each differentiation rule will give you one integration rule. Well, the next page will give you a few more. So these are a few more. The integration of this 1 over 1 plus x squared is arctangent x, because when you differentiate arctangent, you get 1 over 1 plus x squared. So arctangent of x is the antiderivative of 1 over 1 plus x squared according to this differentiation rule. all right? And so on. All the rest are the same, right? So integration of Ex, still Ex plus a constant C, and all this. And if you look at the last one maybe look a little bit strange to you. The last one is the integral of f prime. F prime is df dx, all right? So this one is actually df dx, okay? So this is the integration of df dx over fx, and this is log fx plus a constant c. Where does this come from? This actually comes from chain rule. The chain rule also gives you integration rule. Chain rule for differentiation can also give you a rule in integration. Maybe just to show you a little bit here. Okay, when you differentiate log function, right? Let's say with respect to x. We can't do so because this is a function of a function. We have a function fx inside the logarithmic function, so function of a function, isn't it? So to differentiate function of a function, what do? Chain rule, right? I talk about this in chain rule. So when you do that, then you differentiate this log function with respect to fx first, and then you multiply to the differentiation of fx with respect to x, right? Chain rule, right? And that one, this one, you differentiate a log function, what do you get? You differentiate log x, you get 1 over x, right? So when you differentiate fx with respect to fx, you get 1 over fx. So this is 1 over fx. And this part is just f prime. df dx is f prime. So what does this show? So this rule comes from chain rule, right? So it shows that this log fx is the antiderivative of this whole thing. And this is the integrand, right? This part, right? This is the integrand in this rule. So, and from this chain rule, we know that log fx is the antiderivative of this, which is the integrand, and therefore, when you integrate this, you get the antiderivative, which is log fx. And of course, we add a constant c. So this comes from chain rule. Chain rule also give you this a lot of integration rule, all right? Okay. Then we of course we must have more and more rule to help us, so that we can handle more difficult situation, right? So this this theorem 1.3, it says that if you integrate this a constant a times fx plus a constant b times gx, you integrate this, then we can separate this into two integrals, one for fx, one for gx. And then the constant a and b can also be brought outside the integration. We can just integrate the function first and then multiply to the constant, yeah, for both terms, and then add them together. And all of you have used these rules before, and this rule, of course, help us to find the integral of sum or differences, right, or even multiple, constant multiple, because the constant can be taken outside the integration, all right? So this will simplify the integration somewhat. And it's something that all of you used before. I'm not going to prove to you. I mean, if you want to look at the proof, it can be proven using the definition of definite integral. But let's not go through the proof, and I can refer you to the textbook. You can check out the textbook for the proof, all right? Okay, let's see how we can apply this theorem to do this integration. So this is constant a, which is 3, a constant, times a function fx, plus another constant b times another function gx, isn't it? So using this theorem, then we can split this into two terms. The first one is the integration of cosine after you take out the constant a, which is 3, from the integral. All right, so we can bring it outside. And the second term is the integral of x to the power 8. Again, this constant 4 can be bring outside. So this is a simple use of this theorem. All right, we can split them into simple integration. You integrate this thing all together, the two terms add together. It looks very complicated, isn't it? But after we split into two terms, the terms are simpler than the original one. Okay, the integrands are simpler. Then now we can apply the rule, right? So integrate cosine, you get sine. Just now you saw the list of rule. Yeah. So integration of cosine, you get sine. Integration of x to the power 8. This from the power law for integration. This is x to the power 8 plus 1. 8 plus 1 is 9, and we divide by the same number 9. And of course we add a constant. Why just a constant? Well, I mean this one gives rise to one constant. So this one, when you integrate this one, of course, you get the antiderivative, you add a constant, right? You add a constant. So we say C1. And this one, after you integrate, you also get an integration constant. So we say C2. But the fact that we eventually are adding the two integrals together, meaning that we have two constants, C1 and C2 add together. And that will give you one constant. Yeah? So this one is actually C1 and C2. You add C1 and C2, you get another constant. Therefore, you don't have to add so many constants. You see the two integration, right? Two indefinite integral. Don't put C1, C2 because C1, C2 can be grouped together to form just one constant. Yeah? So just one constant C will do. Don't put C1, C2. And then, of course, this will be the answer. And another simple example, let's say this one. Again, we can apply the same theorem to split this into two integrals. Yeah? So this whole thing split into two integrals, and each one of them we can apply the rule. For the integration of e to the power x, we still get e to the power x. But this part, when we integrate, we get arctangent of x. Yeah? So integration of this one, according to one of the rules, it is the arctangent of x. And then we just add one arbitrary constant or integration constant, c. All right? Okay, so this one is a fraction, right? So something divided by something, but fortunately, it is in the form of f prime over f. So if we consider the denominator to be fx, and then you differentiate. So let's say this one is fx. So f prime will of course be 2x, and that will be in the numerator, isn't it? So this one is actually f prime over f. This is f prime over f when f is x squared plus 1. Okay? And according to a rule we put down earlier on, you see that one, this one? Yeah? F prime over f. Okay? If the integrand is f prime over f, then the result will be log of fx plus a constant. So we are going to apply this. So the answer is log of the function fx plus a constant. This is a rule. So this function is x squared plus 1, so this will be the answer. So it's just a straightforward application of this particular rule, yeah, using this rule. Then we know the result right away. And of course, if you don't want to use this rule, you can use a technique called substitution to do the same thing as well. Yeah? I will be taking you through the integration using the substitution method. But this one, if you don't want to use the rule, you can use the substitution method. You can also use substitution method. In this, you let u to be x squared plus 1, and then you follow through the method of substitution, you will get the same answer without using this rule. Okay? I prefer to use substitution rather than this rule, because substitution, you don't need to memorize anything. Use this rule, you got to memorize the rule, isn't it? So either way, you get the same answer, right? If you use substitution, you do this, let u to be x squared plus 1, and then later on, I take you through the integration by substitution. Then you can come back to this to solve this problem using substitution as homework. You do it yourself. I already give you this u equal to x squared plus 1. Yeah? Okay, another one. This also can also be done using the method of substitution. But here, let's use the same rule. All right, the same rule, which is the integration of f prime over f, right? So we want to integrate this thing, right? So if you observe this, so this one, if fx is tangent, then differentiate tangent is secant squared, right? one of the differentiation rules. Differentiate tangent, you get secant squared. So you can see this is also in the form of f prime over f. So this f is tangent. Okay? So secant squared is the differentiation of tangent. Therefore, the result according to the same rule is log of fx, right? Log of fx, so log tangent x, because the numerator is fx. And then we add a constant. And of course, when we have a log function, then we put absolute sign. We put a vertical stroke to denote this is the absolute sign. Because log for a negative number is undefined. We cannot define the log function for a negative number. So we normally put the two vertical strokes to denote this is the absolute value, because log function cannot exist for a negative number. All right? Okay, just a few more simple examples. So let's say this one. All right, and of course we can arrange it to exponential form. It's just x to the power minus 2 upon 3, and then we apply the power rule, right? So the exponent, again, same as before. We add 1 to the exponent and divide by the same number. We add a constant c, all right? That's right, yeah. Okay, another one, x plus 1, x minus 1. Okay, now this one, none of the rule you can use, isn't it? All those rules you saw just now, you can't use, right? So what we want to do, if you cannot apply the rule, it doesn't mean that you can't solve the problem. What you need to do is just to do some arrangement. Arrange the integrand to something that you can apply the rules. Okay? So how can we do the arrangement for this case? So this one, none of the rule can be applied to this x plus 1, x minus 1. So what we do is, okay, multiply them. You actually get x squared minus 1. And then from x squared minus 1, we can use the first theorem. That is to split the integration into two terms, right? So the first one is the integral of x squared. The second one is integration of 1, right? And to do that, the first one, you integrate x squared, you get x cubed over 3, right? And then the second term is the integration of 1. Integration of 1, with respect to x, you get x, so you get an x here. Of course, it's minus because of this is negative thing. And then you add a constant c, yeah? So the original one, this one, the integrand, none of the rule can be used, but we can do some simple arrangement. Of course, there are many cases for which you need to do more complicated arrangement to arrange it to something that we can still apply the rules, all right? And then the third one, this one, the same thing. None of the rule can be applied to this integrand, right? But we can do some arrangement, split this into two terms. The first term is x cubed over x, which gives you x squared. Second term is 1 over x, which we can put it in exponential form, x to the power minus 1. And then we can separate this into two integration. The first one will give you x cubed over 3 when you integrate x squared. All right? When you integrate x to the minus 1, you get log. And of course, you get a constant c. All right? So that's the idea. If you can apply the rule, it would be something very simple to do. If you cannot apply, never mind, you can do some arrangement. Whether it's straightforward arrangement or more complicated one, you simply have to do it. Or you may be able to apply some of the rules that I have yet to cover. All right? There are more rules to follow. Okay, so this is what we do in indefinite integral. So now let me move on to talk about definite integral. What we mean by definite integral. Okay? Now, this is a definition. The definition for a definite integral within a domain, within a closed interval, a to b, x from a to b closed. Closed, you know this symbol, right? Then, symbolically, we write it in this form. This is the notation to denote this is a definite integral of the function f with respect to x within the closed interval from x equal to a to x equal to b. So this is the symbol, all right? Now, pay attention to the a and b. A and B, we call them limits of integration. A and B, these two things, one is on top, one is on bottom. So this is an integration with respect to x. X is the variable of integration from A to B. So the sequence is important. Whether A is on bottom or on top, it makes a difference. So this is an integration from A to B, first thing. Second thing, this so-called limit of integration corresponds to the variable of integration. And the variable of integration is x. And therefore, this starts from x equal to A to x equal to B, all right? So the limit of integration always must correspond to the variable of integration x. And that is important. I'll tell you why later on, all right? So this is a symbol to denote this is a definite integral. And so how do we define this definite integral? It's defined to be this limit. All right, this limit. Now let me zoom in to tell you what is inside this limit. First of all, FCI. CI is just any point within the interval from A to B. CI is any point. Yeah? So we have C1, C2, we have n number of points from A to B. So these FCI are the value of the function correspond to those points C1, C2, and so on. In other words, these are the y value, right? Remember y is fx, isn't it? So you put ci inside the function, you are getting the value of y. So in other words, this can be considered as yi at the point ci. The value at the point x equal to ci, the value of y will be yi. So that will be the functional value, all right? Delta x is actually the increment in the x direction, okay? So inside here is a product of the y value times the increment in the x value. And we are going to sum up from 1 to n because we are choosing a number of points, C1, C2, up to Cn within the interval. So we form the product, and then we sum them up from number 1 to the last one, number n. And this summation is called the Riemann sum. Just this part is called the Riemann sum, okay? And then the indefinite integral is defined to be the Riemann sum when n goes to infinity. So we are taking the limit as n approaching infinity. When n approaching infinity means we are taking many infinite number of points within the interval and carry out the Riemann sum. And that is defined to be the definite integral. This is a definition, all right? So, and of course, at the end, we are going to take the limit as n approaching infinity. And therefore, the definite integral can only exist when such limit exists. So whether we can find the definite integral will depend on whether this limit exists or not. All right? Okay, this mentions something what I mentioned just now. So lower limit, we call this the limit of integration. The one on the bottom is called the lower limit of integration. The one on top, in this case B, is called the upper limit of integration. All right? So the A and B will define the end point. So we are integrating from x equal to A to x equal to B within this closed interval from A to B. Yeah? Okay? And delta x is, I mentioned to you, is the increment in the x direction. All right? Of course, x is the variable of integration. All right? Fx, this part is called the integrand, just like indefinite integral. The only difference is that now we are integrating the function from a given point x equal to A to another point x equal to B within this interval. That's the difference between indefinite and definite integral. All right? But the definition for for this definite integral is defined to be this limit. All right? Now, let's look at what this limit means, what this indefinite integral means. So what I'm going to do is to show you, is to explain to you a meaning of this part which is defined to be this definite integral. So what's the meaning of the limit of this sum when n goes to infinity? What does it mean? First of all, this function f, this comes from the function fx, right? Fx we can plot, assuming we can plot on a graph. So let's say we have some graph like that. So this is fx versus x. And what I'm going to show you is what is the meaning of this definite integral. When we integrate this function fx from x equal to a here to x equal to b, so what does it mean? So it all depends on what does this limit mean, isn't it? Because this is defined to be the definite integral. All right. Now, first of all, from a to b, let me just show you these are the vertical line. Dot 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 means there are a lot more in between. All right. There are a lot more in between. A lot more in between. That means from the interval a to b, we are dividing the whole interval into a number of vertical strips. You can see strip number 1, strip number 2, number 3, 4, 5, this strip number I, right? And so on until the last one. How many strips are there? How many vertical strips are there? N. There are N vertical strips or panels. Okay? N of them. And for each vertical strip, what do we do? Let's look at a general one. So this is a general one, correspond to the point Ci. Okay? So based on the value x equal to Ci, we can substitute into the function fx to obtain fci, which represents the height of this vertical strip. So fci, this part, is the height of this vertical strip. Right? I mean fx equal to y, right? This is y, right? So this one is y at x equal to Ci, isn't it? Right? So fci represents the height of the vertical strip. Delta x is the change in the x value for that strip. So the change in x value is from the left side to the right side of the vertical strip. So in other words, the width of the vertical strip is delta x. Delta x, the increase in the x direction. So if you look at this part, fci times delta x, that represents the area of this vertical strip. That's the area. Okay? So what is inside fci times delta x represents the area of a general vertical strip within this interval. Okay, now what about the sum? So the sum is summing up from 1 to n. There are n vertical strips, as I mentioned. Strip number 1, strip number 2, 3, and so on. This strip number I, and so on. This strip number n. How many are there? N strips. So the fact that we are forming this so-called Riemann sum, meaning that we are summing up the area. Summing up the area. Because this represents the area of a general strip, so we are summing up for all the strips. So this sum means the total area of all the n vertical strips. Now what does this limit mean? So when we are taking the limit as n goes to infinity, what is n? N is the number of vertical strips. Yeah? This is n. So if n goes to infinity, that means we are taking infinite number of vertical strips within this interval from a to b. So what it means is that within the interval from a to b, we divide this into infinite number of vertical strips. And then we sum up the area of each vertical strip. So that's what this limit means, right? So n tends to infinity means there are infinite strips. Infinite number of vertical strips. We sum them up, right? And then we say there are infinite number of them. So that means you can see from this diagram, this whole limit is defined to be the definite integral, and that is actually the area under the curve. So what it means is that definite integral from A to B simply means the area under the curve fx from A to B. That is what it means. Okay? So that's the definition, right? So we actually interpret the definition. This is a definition of definite integral. And then the interpretation for that is it actually represents the area under the curve. So this is comes from the definition of definite integral. And therefore, the first method that we are going to use to evaluate definite integral is based on this method of working out the area. Because the area, according to the definition, the definite integral is the area under the curve. So let's look at. Okay. So let's look at this. Well, before the example, maybe just to introduce to you a few theorems. This example. Okay, maybe we go through this example a bit later, right? Maybe let me just continue from here first. Now, based on, so this one, the definition of this definite integral as the area under the curve is the first method that you learn how to evaluate a definite integral. Okay? And of course, if the integrand is more complicated than that, let's say if it is a constant c times a function fx plus another constant d times gx, you want to form the definite integral, then you can do like indefinite integral. We can split into two terms and take out the constant c and d outside, right? I mean, in definite integral, we did that so a while ago. But for definite integral, it's the same thing, right? Except now all the two terms are also definite integral. The first one, a to b, x from a to b. Second one, also the same from a to b. All right? Well, another rule, this one is new for this. This one is, we have the same one for indefinite integral, right? But this one is for definite integral. So the second one in this theorem says when you integrate a function fx with respect to x, or in the x direction, from a to b, you can split into two integrations. The first one from a to c, and then the second one from c to b, when c is inside the interval. I mean, if you think of the area, that is straightforward, isn't it? Because when you integrate that, yeah, so when you integrate this from a to b, you have a constant c inside. So the integral, the left-hand side is the entire area under the curve from a to b. Then we can integrate from a to c first, this part. So to get this, the area of this part from this term. And then from c to b, so this part, which represents the area of this part. And then we add them up. So the result is the same, isn't it? The result is the total area under the curve a and b. Then why do we need to do that? Well, I mean, why don't we just solve this problem in one go instead of split them into two? Well, sometimes we have no choice. Sometimes within the interval a to b, maybe there is a discontinuity somewhere. Therefore, we cannot integrate the function from a to b directly. We've got to split into two. I think we are going to have some example based on this, all right? Based on this concept. Okay, before we look at the example, just to introduce two very useful definitions, all right? The first one, the integration from b to a is the integration of a to b, but then you have to add a minus sign in front, meaning that I mentioned to you already, the order of the limit of integration is important. Which one is upper limit, which one is lower is important, right? So if you reverse the direction of the integration, instead of from b to a, you use a to b, then you're going into the opposite direction, and therefore, naturally, you have to add a minus sign in front. Yeah. So this sometimes can be useful also. So it allows us to change the direction of integration from a to b to a, and vice versa. So we are free to alter the sequence, alter the direction of integration, whether from b to a or a to b. What you need to make sure is that there is a minus sign in between, yeah, to relate the two. And then the second one, if we are integrating a function from a to a, we get nothing. Yeah? And that is understood. I mean, you think of this being the area under the curve. Right? That is what the definite integral is defined to be. So when you integrate from the same point to the same point, what's the area under the same curve from the same point from x equal a to x equal a? Nothing, 0. The area will be 0. So obviously this is how you get a 0 here. Oh. Okay? Now, I was saying that this theorem 4.2, the second one here, is useful when there is a discontinuity in fx within the given interval from a to b. You have to split into 2. Well, I mean, this diagram shows you one such case in which you have to split the interval from a to b into 2 subintervals, from a to c and then c to b. A to b, yeah, a to c and then c to b. Yeah? Okay? That is when the function is discontinuous. So let me define this for you. We call a piecewise continuous function when it behaves something like that. All right? I mean, this is one typical piecewise continuous function. Piecewise, that means it consists of a number of pieces. Continuous, that means each piece is continuous. But the entire function is discontinuous, as you can see here. For this case, there are 2 discontinuity at these two locations here, right? Here and here. There is sudden jump in the functional value. It changed from this value, suddenly jump up to this value, and at this point, at this value of x, the value suddenly drop from this value to this value. So there is a sudden change of value at these 2 locations. So we have 2 discontinuities for this function. But anyway, this is called a piecewise continuous function. And if you want to integrate a function within an interval, you have this continuity. Then you have to split the interval into subinterval. Okay? So in this case, if you want to integrate from a to here, let's say b, then you can split. Let's say you integrate fx from a to b. Then you have to split into 3 from a to b, a to c, and then c to d, and then d to b, right? You cannot one goes integrate from a to b because there is a discontinuity. This function, this integrand, is described by different expression. The expression for this piece, for all the different pieces will be different. So that's the reason why we have to split into a few indefinite integral when this situation arises. Okay, now let's look at this example. Now, what I have shown you is the definition of definite integral. So we are going to use the definition of definite integral to evaluate this integral. All right, so we are going to integrate this function from 0 to 3. And this function is described by two expressions. 2x when x is less than or equal to 2, 1 when x is bigger than 2. So we are going to use the definition for this so-called definite integral to work out the result. Therefore, we make use of the area under the curve to evaluate this integral, okay? And to do that, then we sketch the function, okay, which are quite easy to sketch. Fx equal to 2x from, since we are integrating from 0 to 3 outside this interval, we don't care how it looks like, because we just want to integrate fx from 0 to 3, right? So from 0 to 2, the function is described by 2x. Therefore, this line, this is 2x, straight line, right? Going up, the slope is 2, right? Quite steep. And then when x equal 2, that is from 2 to 3, the function is described by this constant 1. So from x equal 2 to x equal 3, will be like that. When x is bigger than 3, we don't worry. It's outside the interval from 0 to 3, right? Okay? So according to the theorem 4.2, number 2, from 0 to 3, integrate from this point to this point, we got to split into 2 parts because different part is described by different function. So first of all, from 0 to 2, and then from 2 to 3. Okay? From 0 to 2, the function fx, the integrand here, is 2x. From 2 to 3, the function or the integrand is 1, the constant 1. Okay? So, but what we know is this. This definite integral from 0 to 2 represent the area under the curve. Therefore, the first integral is the area of the blue triangle, isn't it? Whereas the second integral, by definition, it represents the area of the pink color, I think is a square, which can be done quite easily. For the first integral is the area of the triangle, so it's half times 2 times the height, which is 4, we get 4. And the second integral is the area of this square, which is just 1 times 1, give you 1 here. Therefore, the result, when you integrate 0 to 3, you just add them together, 4 plus 1, you get 5. Okay? So this one, we are using the definition of definite integral to find the answer. But you can see that this way is going to be very troublesome. If the function is not so straightforward, these two functions are very simple, 2x and 1. So we can use the area, no problem at all, quite easy. What if the function is very complicated? Then, of course, you can still apply this technique, but this is going to be very difficult, isn't it? It all depends on the integrand, all right? So this will lead us to a very important, the fundamental theorem of calculus. Now, I think you should realize when you evaluate a definite integral using the definition, that is to say, use the area under the curve, is going to be very difficult in general, unless the integrand is very simple. Therefore, we need something better than that. And this fundamental theorem of calculus, there are two parts. Part 1 will offer you a much easier way to evaluate a definite integral. We don't use the area under the curve, okay, which is very troublesome. So this theorem says, first of all, the function f, the integrand, fx is the integrand, right? So the integrand must be continuous within the interval from a to b. Must be continuous. If it is not continuous, you can't use this fundamental theorem. You can't use, okay? So if the integrand is continuous, then if we know fx is the antiderivative, if we know the antiderivative, just like in definite integral, right? Okay, in definite integral, we always make use of the antiderivative to solve the problem. So that is why every differentiation rule will give you one integration rule, because differentiation rule will give you all the antiderivatives, right? So we can work this out like the indefinite integral by using the antiderivative of the integrand, all right? So long as you know the integrand, so long as you know the antiderivative of the integrand, then you just evaluate this, which is fx. You just have to evaluate this one, which represents fb minus fa. In other words, you evaluate the antiderivative, the capital F, at the two end points, x equal to a and x equal to b, and then you take the difference. The one that corresponds to the upper limit minus the one that corresponds to the lower limit, all right? And this is called the fundamental theorem of calculus. Without that, we are in trouble. We can't use area all the time, right? Can we? We can't, right? So this one will give us a very simple way to evaluate definite integral, making use of the antiderivatives. All right? Okay, now if let's say f is discontinuous, then you can't do that. But in that case, we have theorem 4.2, number 2 to help us. So let's say if we have a piecewise continuous function, just like that, then we can use this theorem, right? This one, to split the integral into a number of integrals on which the function or the integrand are always continuous within each subinterval, then we can still apply this fundamental theorem of calculus to evaluate each of the integrals, isn't it? So we can do that, right? Okay. So if it has a jump or a discontinuity at a point x equals c, then we split this into two, from a to c and then from c to b. Right? I went through that, right? And then we can still apply the fundamental theorem to solve the problem. Okay, the proof, I think I don't go through. Let's skip the proof. You can find the detail of the proof in the textbook, all right? So how do we do that? Use the fundamental theorem. So in that case, we don't use area under the curve, huh? Don't use area under the curve. I mean, I explained this to you because this is the fundamental definition, the definition of the definite integral. And second reason is that hopefully today, towards the end of the lecture, I can cover the numerical integration, which is based on the definition of definite integral, based on the area under the curve. We can devise some numerical technique to solve this integration problem, which are very difficult or not possible to solve analytically. All right? Then we have numerical method to help us, which is based on the definition of definite integral. Okay, so let's look at this problem. So we integrate this from 0 to 2, all right? Then we know the antiderivative of x squared minus 2x is 1/3 x cubed minus x squared. You all know that, right? I mean, if you want, you can split this into two integrals, but I think for simple cases like that, it's not necessary. You can split, up to you, okay? So the antiderivative of x squared minus 2x is 1/3 x cubed minus x squared using the power rule for integration, isn't it? Yeah? And according to the fundamental theorem of calculus, part 1, then we just have to use the antiderivative and then put in a limit from 0 to 2 and then work out the difference of the antiderivative at the two endpoints. This one is correspond to the upper limit. Yeah, when you substitute x equal to 2 inside, you get 8/3. When you substitute 0, you get 8/3 minus 4. When you substitute 0, you get 0. So this corresponds to the value of the antiderivative when x equal to 2, the upper limit. And this corresponds to the lower limit. So you take the difference. So that is the fundamental theorem of calculus, right? So you get the answer, minus 4/3. We don't have to worry about the area under the curve anymore, right? Okay, another one, this one. Okay, integration from 1 to 4. Well, first of all, when you apply this fundamental theorem, you've got to make sure that the integrand must be continuous, all right? So this is the integrand, which is written in exponential form, is x to the power half minus x to the power minus 2 is the same thing, right? So by inspection, you know this is continuous, isn't it? Because any x value between 1 and 4, you always can find a single value for this one, for this function. Yeah? And therefore, it is continuous within the interval. Outside the interval, never mind. Well, obviously, when x equals 0, this is discontinuous, isn't it? When x equals 0, you have 1/0 here inside the integrand. So the integrand is undefined at x equals 0. But that doesn't worry us because x equals 0 is outside the interval. We don't worry. We only need to ensure that the integrand is continuous within the closed interval from 1 to 4. Yeah? Okay? So now, to integrate this one, we know the antiderivative. So we work it out using the technique for indefinite integral. All right? So integrate term by term, then you have that. And then now substitute the limit of integration. Substitute 4 inside, you give you the first, this part. Substitute the lower limit, x equal 1 inside, we get this part. Subtract them according to the fundamental theorem, we get an answer. Well, since integration represents the area under the curve, so together with the fundamental theorem, we can use it to determine the area under the curve, making use of this definite integral. Okay? So we want to find the area under the curve y equals sine x from 0 to pi. Obviously, from 0 to pi, the function sine x is continuous. Well, sine x is continuous everywhere anyway. Yeah? So, by definition, the definite integral of sine x from 0 to pi represent the area under the curve from 0 to pi. So to work out the area, we can apply the fundamental theorem. Okay? So we just integrate sine x. You do that, you get minus cosine x. And then put in the limit of integration from 0 to pi. So when x equals pi, that is the upper limit. X equals 0, the lower limit, you get minus cosine 0. Subtract them, you get 2. So this is the area under the sine curve from 0 to pi. Now, without the fundamental theorem, how do you find the area under the curve? This sine function. Difficult, isn't it? Maybe you can plot a graph and then count the number of squares under the graph. Do it graphically. But that is not accurate, right? So this way, using the fundamental theorem, one can work out the area quite easily. And in fact, this example already show you one typical application of integration. That is to evaluate the area under the curve. One can apply this definite integral. It's one of the application of integration, actually. All right. Okay. Another example. This one is an exponential function. We integrate this from 0 to 4. First of all, before you apply fundamental theorem of calculus, make sure the integrand is continuous within the given interval from 0 to 4. And that one we can see by inspection, right? So from 0 to 4, the exponential function always has a value, therefore continuous. And now we can apply the fundamental theorem. And this is the antiderivative of the integrand. So put in the limit of integration from 0 to 4, x from 0 to 4. Then according to the fundamental theorem, we get this thing, and your calculator will give you a value. It's roughly 0.49983. All right. Just another one. So this one again is continuous. Right, this integrand continuous, and therefore we can do as usual. So when you integrate that, the constant 2 can be brought outside. So we integrate 1 over x, and according to one of the rules, you get log of x, absolute x. And then put in the limit of integration according to the fundamental theorem, you get the answer. So again, it's just another straightforward example. All right. Now, all the examples you saw so far, they always have constant limits of integration, isn't it? You see, from -3 to -1, from 0 to 4, and so on, from 1 to 4. Yeah. So the two limits of integration are constant. What if the limit of integration is not constant? Let's say for this case, we integrate this from 1 to x. That means we integrate this from t equal to 1, right? T is the variable of integration. So integrate from t equal to 1 to t equal to x. So x can be any value. All right? Can be any value. So we just perform as usual. All right? So even though the upper limit is a variable, never mind. Whether upper limit or lower limit, it makes no difference. We just evaluate as usual using the fundamental theorem of calculus. All right? So integrate this, you get 12t to the power 6 over 6, and then the limit of integration is 1 to x, so this also 1 to x, and then put in t equal to x, right? T equal to x, then you have 2 t to the power 6 here, this term, and then subtract away the antiderivative correspond to the lower limit. When t equal to 1, then you get 12 over 6, which is 2. So give you this one, yeah? 2 times 1, it is 2, right? Okay? So if the upper limit is a variable, makes no difference. We just do as usual, whether they are constant or variable. For that matter, If the lower limit is variable, you just do the same thing. Maybe both are variable. From x1 to x2, let's say you integrate something from x1 to x2, you just repeat the same thing, no difference at all. All right? Okay, then this is the second part of the fundamental theorem of calculus. So the part one of this fundamental theorem is very useful, right? We don't have to use the area under the curve to evaluate this integral. We can use the part one of this fundamental theorem of calculus. Now, part two of the fundamental theorem of calculus serves another purpose. Let's see what it is about, all right? It is also called the fundamental theorem of calculus. Therefore, we say part one, part two, because both are given the same name, you see, all right? Again, first of all, the function f must be the integrand. You see that we have an integral here, right? So the integrand ft must be continuous within the interval, okay? And then this fx, capital big Fx, is actually the definite integral of this ft, okay? All right? Then, of course, imagine if you can evaluate this integral from a constant a to a variable limit of integration, just like the last example, the result will be a function of x, just like the last example. You see a function of x. When you integrate from a constant to a variable x, the result will be a function of x, isn't it? Same thing here. So integration of this ft with respect to t from a to x, this will give you a function of x, which is big Fx. All right? So what this fundamental theorem part 2 say, the derivative of Fx, this part, you see, right, or f prime, which is the same as the derivative of this integral, right, because Fx is this integral. And the theorem say this is just Fx. Okay? dfx dx, this part, is definitely this one, because Fx is this one. So you differentiate both sides, the left side, differentiation of left side, this one, differentiation of right side is this one. And the theorem says this is just equal to Fx. That means it's exactly the integral, sorry, the integrand. Is exactly the integrand with the variable t now replaced by the variable x. So what's the use of this theorem? I told you just now, if you have an integration, something like that, integrate from a constant to a variable x, you end up with a function of x. This theorem gives you the derivative of the integral. This is a function of x, right? This is function of x, fx, like this one. This is our fx. For this, in this example, you integrate this, you get a function of x, which is big Fx. All right? So, you differentiate the integral with respect to x. The theorem says it's just the integrand as a function of x. So that's what it says. Very simple. Now, bear in mind this thing. Maybe I just circle it. This one, you are differentiate this integral with respect to x, right? And this has to be the same as the upper of limit of integration. These two circles must be the same. That means when you want to differentiate this integral, you can only differentiate it with respect to the variable appearing in the upper limit of integration. Yeah, you follow that? This is upper limit is x, and this derivative must be with respect to x, so that the fundamental theorem part 2 apply, and the result become a function of x. Yeah, circle this one as well. So these three things must be the same. Now this constant a, not important, constant. This constant a, whether this constant is 1, 2, 3, whatever, so long as constant, this theorem apply. You always get Fx. In other words, this constant a doesn't play a part. So long as it's constant, it doesn't really matter what is the value of this constant. So that's what this theorem says. Okay? So the upper limit of integration must be x. Yeah, must be x. Upper limit of integration. And lower limit must be a constant. Lower must be a constant a. All right? Then what if they are not? Can we apply the theorem? Well, directly you cannot, but indirectly we can. Maybe we can make use of chain rule, and maybe we also need to split the integral into the sum of two integral. After that, we can still make use of the fundamental theorem. So this part will be shown in examples 5.8 and 5.9. All right? But if the upper limit is x and then we differentiate this integral with respect to x, then according to the theorem, the answer is very simple. It's just fx. Right? But when this is not a variable, when the lower limit is not a constant or something like that, then we got to do something special about it, do some arrangement. Arrange it to something that eventually this part 2 of the theorem can still be used. All right? We need to do some arrangement. This part. We need to do some special arrangement. Change it to something that we can still apply the theorem. All right? Okay, first of all, let's look at this example, which is straightforward. Now, this is x. Let me just do like that. This is x. Okay? And this one is actually dfx dx. So you see in this one, we are given this integral, right? This integral is a function of t from 1 to x. So from a constant a equal to 1 to a variable x. And we want to find dfx dx, right? That is f prime. So this one. These two are the same, are the same. So this is exactly what is described by the theorem. ddx of the integral. ddx of fx, which is the integral. And you can see here, x, maybe I circle another circle here. X are the same. Tally with what the theorem is about. Take a look here. It's the x, right? Therefore, what is the derivative of this integral? According to the theorem, is simply fx. So whatever ft, you just rename the variable t as x. That's all you do. Replace t by x. Then you get fx. Right? So here, do the same thing. ft is t squared minus 2t, the integrand, right? This one. So just replace t by x. You get x squared minus 2x plus 3, because we replace ft is this one, so fx just replace t by x. You get x squared minus 2x plus 3. So that will be the answer. So we don't have to do any work. This is the differentiation of this integral already. Now, maybe homework for you. Verify. Homework, Is this correct or not? That means homework. Is the answer correct? So what do you do? Carry out the integration. Yeah, you can do this integration quite easily, right? Integrate this. Yeah, integrate this. Now, to get the answer, we don't need to do any integration, isn't it? We just get the integrand, which is ft, and then we just replace t by x. Then we say that this is d capital F with respect to x. So integrate this, you get a function of x, you get fx. And then differentiate to find df dx yourself. See for yourself that you get the same answer. But using the fundamental theorem part 2, we don't have to go through this process. Okay? All right, that's the use of this part 2 of the theorem. Maybe we take a break before I show you. After the break, I'm going to show you this part. Let's say if the lower limit is not a constant, or if the upper limit is not x but something else, what do? We are going to apply chain rule, and we are going to split the integral into a sum of a number of terms to handle the situation. That one I will discuss after the break. Yeah. So let's say 15 minutes. 4, 3 plus 15. 5, 8. So 3, 5, 8. 3, 5, 8. We start our lecture again. 15 minutes from now. Okay. All right, let's continue. So you see when the lower limit is a constant and the upper limit is the variable x, then to obtain the derivative of such integral with respect to the upper limit x is straightforward. What you need to do is to get the integrand, and then replace the variable t as x to obtain fx, right? To obtain fx, and that will be the answer. That will be the differentiation of the integral, all right? Okay, the problem is sometimes the upper limit may not be x. Sometimes the lower limit may not be constant. Then how do we handle such situation? Then we have to do something to arrange it. Yeah, as I said, we got to arrange it to something that we can still apply those theorem or whatever rules for integration. Now let me illustrate this to you by examples, which is, I think, is the best way to illustrate to you the method of doing it. So we are given the integral, all right? So this is the integral of cosine t from 2 to x squared. So the upper limit is not x. Therefore, we can't apply the theorem. The theorem, the upper limit must be x, and then it will give you the derivative of the integral with respect to x. Well, of course, the lower limit must be a constant. Yeah. So it doesn't conform to this form. And therefore, to do that, then we have to do something about it. So first of all, the upper limit cannot be squared. It must be just a variable. Of course, this is not x. Therefore, let's rename this as another variable, u, let's say. All right, u. So we are going to let u to be x squared. So now the upper limit becomes u already, which is a function of x. Okay? Now, if you integrate this thing with an upper limit being u, then obviously you get a function of u at the end, right? Imagine if you integrate this, okay, this one we can integrate quite easily. Integrate cosine, you get sine, of course, right? But when you put in the limit of integration, eventually you get cosine u minus cosine 2, right? So definitely it's a function of the upper limit of integration, the variable u. So this one is a function of u. No longer a function of x, right? After we make this substitution, let u to be x squared, then this integral become a function of u ultimately. The original one is still a function of x, right? When you integrate this, you substitute t equal to x squared as the upper limit, of course you get a function of x. So this is a function of x. Now we turn it to become a function of u. So this becomes a function of u, all right? Now if this is a function of u, according to the fundamental theorem, we can find the derivative of this with respect to the upper limit u, not x. So if we take you back to this, so we can find the differentiation of the integral with respect to the upper limit x. You see this x, this also x, right? Therefore, if we do that, then we can differentiate this integral with respect to the upper limit u, not x. All right? We can only get the differentiation with respect to u. But according to a chain rule, df dx can be written as df du times du dx. Okay, because f is a function of u and u is a function of x. So it's a function of a function, isn't it? Yeah, big F is a function of u. You can see that, right? I just mentioned to you. So you do this integration. This big F is a function of u, but u is a function of x. U is x squared. So this is a function of a function. So to find df dx, we can apply the chain rule, which say this is df du times du dx. And both differentiation on the right-hand side here, df du, we can find using the fundamental theorem of calculus part 2, because this is u, right? And this du dx we can find easily, because we know u in terms of x. All right? So that is what happened. So long as the upper limit is log x, then you just let that to be u, and then apply chain rule, you can still find df dx. What we ultimately want is df dx. No longer df du, right? But we can make use of df du. Okay, Then df du, this part, this integral, we differentiate this with respect to u. So that is exactly what the fundamental theorem can give you. So what is the answer? So when this is u, then the answer will be fu, isn't it? So this three circle, right? We are talking about mathematics. Okay, so this becomes a function of u. Therefore, ft is cosine t. So what is fu? It's just cosine u, isn't it? So cosine u is here. All right? So this is the differentiation of the integral. This comes from the fundamental theorem, cosine u. And then, of course, according to the chain rule, we have to multiply this to du dx. And du dx from here, u equal to x squared, so du dx is 2x. So the answer is this one, 2x cosine u. And of course, we don't want u to be there. We want everything to be in terms of x. So we finally put back u in terms of x. U is x squared. Put it back here. So this is actually cosine x squared. And that will give you the answer. So this is the differentiation of this function, this integral, with respect to x. All right? So we apply the chain rule. So that is how we get around this problem. Another example. This case, we have one more trouble. In addition to the upper limit not being x but x squared, just like the last example, in this case, the lower limit of integration is 2x, also a variable, is no longer a constant. Okay? So upper limit is not x, lower limit is not a constant. Then how do we find the derivative of the integral? This one, big F prime x, right? Is the differentiation of this with respect to x. So what do we do? Now, first of all, if the upper limit of integration is log x, like in the last example, this one, we know we can apply to the chain rule to handle the situation, no problem at all. We don't worry the upper limit being not being x anymore because we have the chain rule to help us, all right? But the lower limit, we must change it to a constant, otherwise the theorem cannot apply, right? If you look at the theorem, you see the lower limit must be constant. This one must be a constant, huh? If it is not a constant, a variable, then the theorem cannot be applied. Therefore, we don't do some arrangement. So what do we do? Now, the integration of this integrand from 2x to x squared, we can split into two integrals. From 2x to a constant 0, and then from 0 to x squared. We can do that, right? Remember one of the theorem earlier on? We can split the integration from a to b into two parts. First part from a to c, and then second part from c to b, right? So we are using that theorem. To split this integration, make use of an intermediate value, 0. So that the integration is now from 2x to 0, and then from 0 to x squared. So they are the same. That is according to theorem 4.2, number 2. Okay, take a look there. All right? We can also apply one of the integral I showed you earlier on, in which the limit of integration can be interchanged. Instead of from 2x to 0, we change it to 0 to 2x. We reverse the direction of integration. In doing so, we have to add a minus sign in front. Remember, if you change the sequence of the limit of integration, then you are altering the integral by a negative sign. So we add a minus sign in front. Why we do that? Well, first of all, if we want to apply the fundamental theorem part 2, the lower limit must be constant. This one, upper limit constant, not so good. So we reverse it. Bring this down to the lower limit from 0 to 2x, and then we can add a minus sign in front. Why we do that? Well, because we just want to apply the fundamental theorem, which requires the lower limit to be a constant. So we do this arrangement, right? And for the second integral, we are fine. The lower limit of integration constant, 0. So now you see these two integrals, 0, 0. Lower limit, they all constant. Okay, fine. Now left with the upper limit. Upper limit is no longer x for both, but this one, fine. We can use the chain rule as you saw in example 5.8, just now that one, to handle this situation when the upper limit is not x, but something else. So we apply chain rule, right? Okay. All right, so let's work out the first. There were two integrals. The first one here and the second one here. Let's work out one by one. Let's look at the first one, this one, this one. So this one, the upper limit is 2x, lower limit is x. Sorry, 0. Yeah, 0 to 2x, right? So what do? So we differentiate, when we differentiate this integral, we apply chain rule. So we differentiate the integral with respect to u first, which is the same as the upper limit. You see this u here and this u are the same. And the lower limit is a constant. When this happens, fundamental theorem part 2 can be used. All right? The upper limit corresponds to the variable that we are differentiating with respect to. The lower limit corresponds to a constant. Whether this constant is 0, 1, 2 or not doesn't really matter. Then we can apply the fundamental theorem to find this derivative. All right? But of course, according to chain rule, then we have to multiply this to du dx, right, to obtain d dx. So this d du times du dx, right? So this part is chain rule, all right, chain rule. So now apply fundamental theorem. Of course, here you can see that our upper limit changed to u. Obviously, u is 2x, right? Come from here. We let u to be 2x. So we end up with an integral like that. And therefore, now we apply the fundamental theorem. So this part, the derivative with respect to u, when the upper limit is u, is what? This is ft. So again, we end up with fu, right? So fu, you just change t to u. So this becomes u squared plus 1. And of course, we multiply by du dx according to chain rule. And du dx is 2. So we multiply by 2, we get something like this. Okay? Now the second integral. This one. Okay? And just work it out in the same way. For this case, we let the upper limit to be u. So u is x squared here. All right? And now this become, according to chain rule, is d du times du dx, same as before. And this one, we can apply the fundamental theorem. So we replace t by u, so this is become square root of u squared plus 1. And then du dx, according to this, is 2x. All right? So we can find that. And finally, substitute these two integral, put it back here. That will give you the answer. All right? So that's the answer you get at the end. So if the limits are not constant and they are not x, we can apply, this technique. Maybe split the integral into 2. At the same time, we can make use of chain rule to solve the problem. All right? No problem at all. Okay, one more example. In this case, we are given a function of x, all right, in the form of a definite integral. So when you integrate this, you get a function of x, all right? So this is a function of x, and we want to find an equation of the tangent line to this function, big Fx, at the point when small x is 2, okay? So to find the equation of the straight line, we always need to know two things. Remember, the slope and also one point, any point on the line, right? So let's find the slope first. The slope of this line is f prime because the function is this fx. So we want to find the slope. The slope is f prime. So to find f prime, we make use of fundamental theorem part 2. That means we differentiate this with respect to x, isn't it? And to do that, we don't have to do the integration and then differentiate. Straight away, we can apply this fundamental theorem part 2 with the help of the chain rule, of course, because the upper limit is not x, right? So like the previous example, to do that, we let x squared to be u, right? We let x squared to be u, so this upper limit become u, and then we can differentiate this with respect to u, and according to fundamental theorem part 2, this will be log u cubed plus 4. Right? Log u cubed plus 4 here. U is x squared, so this becomes log x squared cubed plus 4. Because u is x squared. We let u to be x squared. And according to chain rule, we got to multiply this to the differentiation of x squared. All right? So this is 2x. Okay? 2x. and eventually this is the slope on the function, on the curve fx, okay? And of course, since we are looking at x equal to 2, then substitute x equal to 2 inside. We know the slope of the tangent line required, which gives you 4 log 68. Okay, when x equal to 2, just put x equal to 2 here and here. All right? So the slope is found. Now we need to find one point on the tangent line. The tangent line passes through the point when x equal to 2. We must know the y coordinate as well. Yeah? To find one point, you need to know the two coordinates, x and y. X is 2, so what is y? Well, this is y, right? Here. This is y. Y equal to fx, right? So substitute x equal to 2 inside. Here. Upper limit here. X equal to 2. So this integration is the integration from 4 to 2 squared. Why do we do that? Well, we want to find the value of y correspond to x equal to 2. So when x equal to 2, the upper limit becomes 4, right? This becomes 4. So it's an integration of, the y value correspond to x equal to 2 is the integration from 4 to x squared. Therefore, from 4 to 4. 4 to 4 obviously is 0. When you integrate something from a to a, it is always 0, isn't it? So you get 0. So that means the tangent line passes through this point 2, 0, x equal to 2, y equal to 0. And the slope is what we have found using the fundamental theorem part 2, which is 4 log 68. And therefore, we can form the equation of the straight line, this one. So that's the answer. All right? Okay. Now, earlier I was saying that one of the earlier example we can solve by this technique called substitution. Instead of using the rules that we saw just now, we can apply this technique called the integration technique. All right. So let me take you through this integration technique, which is very useful. Well, it's one of the simplest integration technique, but in many integral you need to make use of that. All right. Okay. Now some preliminary, some background on it. In substitution, we are going to change the variable of integration from x to u. Okay. In an integral, we have the integration with respect to x, isn't it? That means the variable of integration is normally x, but sometimes we can't integrate. If we integrate with respect to x, we can't. We have some problem. And maybe using this technique called substitution, whereby we are going to change the integration variable. Instead of integrating something with respect to x, we want to change it to an integral with respect to a new variable, u. All right? And to do that, we need to relate dx to du. Right? I mean, just to show you, maybe let's go look. For example, let's say if you look at this integral, not this example, all right? But just look at this integral. Look at this integral. This integral, the variable of integration is t, right? We integrate something with respect to t. And in substitution method, we are going to change this variable to something else, to u, let's say. Therefore, we want to change from dt to du. If this was x, like many earlier examples, let's say you integrate this with respect to x, right? And if you want to change this to du, another variable of integration, then we must find how dx and du are related. All right? So this is the part that this is what it shows. Yeah, we need to find a relationship between du and dx so that we can change from dx to du. All right? And this comes from this relationship. Du is du dx times dx. How do we know? Well, I'm not going to prove it to you, but you can think of it this way. Think of dx being cancelled out, so the left side du, the right-hand side still du, so the two things are equal. Or you can think of this way. Du dx is du dx, of course, then this dx can be thought of being moved to the right-hand side. So du is du dx times dx. All right? So either case, it shows you that this du equal to du dx times dx. And this is what you need in order to change from dx to du in a substitution. We want to change x to become u, all right? And therefore, if you do that, then eventually an integral of this form, an integral of a function of x with respect to x, is now changed to another form, become the integral of a function of u with respect to u. You see, the variable of integration x is now changed to u, and correspondingly, we must change x to become a function of u so that we can carry out the integration, right? Okay? All right, how do we do that? Okay, let's look at this example. Integration of x cubed plus 5 to the power 100 times 3x squared, and then we want to integrate this with respect to x. Okay? By the way, this is an indefinite integral. There isn't any limit of integration. So at the end, we are going to have an integration constant at the end, right? Okay, but how do we do that? All right, now if you observe this integrand, there are two functions. One is x cubed plus 5, the other one is 3x squared. Now if you differentiate this x cubed plus 5, you can see that this gives you 3x squared, this one. Okay? Therefore, we let u to be this function. Okay? We are going to make the substitution u equal to x cubed plus 5. Why we do that? Because the differentiation of this one will give you this one. I will come back to this point in a short while. Right? How do you select the expression to substitute? In this case, we select x cubed plus 5. We let this to be u. All right? So now, going through this expression, du is du dx times dx. So now we can differentiate. Du dx is what? I mean, u is x cubed plus 5. So du dx is 3x squared. So this part is 3x squared. So 3x squared times dx. All right? Okay? So now we go back to the original integral here. We want to change all the x to become u. This one, no problem. This x cubed plus 5 is u, right? U. So this becomes u to the power 100. Okay? Then what about this part? Oh, this part, no problem, because here we have 3x squared dx all together. This dx together with 3x squared become du. So this whole thing now become du. So all the x gone. Eventually become an integral containing the variable u only. No more x inside, isn't it? All right? This become u. This whole lot become du. So become something very simple to do. Yeah? So this become u. This become, the whole thing become du. So this is u to the power 100. It's the integral of this with respect to u. And that one can be done quite easily. So using the power rule, this become u to the power 101, divided by 101. And of course, do not forget the arbitrary constant or integration constant c here. All right, for any indefinite integral, you must insert a integration constant c there. And of course, we want the result to be in terms of x. Therefore, put it back. U is x cubed plus 5. So change it back to be function of x. We get the answer. Is this answer correct? Well, we can check. Let's differentiate. What it says is that if this answer is correct, that means if we differentiate this answer, which is so-called the antiderivative of the integrand, we are supposed to get the integrand, isn't it? So differentiate this. Differentiate this, the answer with respect to x. If you follow through using a chain rule, all right, then you can see that it's actually the original integrand here. So that means the answer is correct. Okay? So the original function, like that, x cubed plus 5 to the power 100. Now, without this method of substitution, how would you integrate this? There's one way. Without using this method of substitution, how do we integrate this? You can do this, you know. This one is x cubed plus 5 times x cubed plus 5 times another x cubed plus 5. How many of them? 100 of them. Expand them. You know, expand them. Then you get a very long polynomial. And then split into term by term. You can then integrate term by term using the power method. You can do that, right? Can be done. Do you want to do it as homework? You see, it's very troublesome. In this case, it can be done. I mean, it takes days, and then you still make mistake, you know. But it can be done, isn't it? But using the method of substitution, you see how simple it is. It becomes an integral of x u to the power 100 times with respect to u. Becomes something very simple, isn't it? So that is why this method is very useful. In many cases, we can apply this technique called method of substitution. All right. So in method of substitution, what do we do? Here is the general method, the general process that you should think about. Okay? First of all, as you have seen in the last example, when we make the substitution, you have to make a correct choice of the new variable u. Just now that one, we let x cubed plus 5 equal to u. How do we know? How do we know? Right? So there is a clue here. The clue is that usually we take the innermost expression. Inside the integrand, you have functions, right? Let's say this one. Inside the integrand, we have function x cubed plus 5 to the power 100. We have function x squared and so on. Well, basically the two functions. And then what do? Usually is that you try to look for a certain function inside the integrand for which you can obtain the other function by differentiation. For example, just now there's this one. If you let u to be x cubed plus 5, you differentiate, you get 3x squared. The number 3 doesn't really matter, it's a constant. You get x squared, right? You differentiate x cubed, you get x squared. The number 3, it doesn't really matter. Which is the same, which is another function inside the integrand. And therefore, you normally let that to be u, right? So this is the usually what you need to do, yeah? So you just make a choice. If you look for the inside the integrand, something that you differentiate, then it can generate another function inside the integrand. Then you let that to be the variable u, all right? So in that case, x cubed plus 5 is the inside term. Inside this x cubed plus 5 to the power 100. Usually we let the something inside to be the new variable u. Okay? And this part is perhaps the most difficult one. How do we choose the correct variable u to use? Okay? These are the most difficult part. In case you choose wrongly, then what happens? Of course, you will get stuck somewhere. You choose wrongly. You don't choose x cubed plus 5 being u. Maybe you choose x squared to be u. You let u to be x squared. Then you follow the method. You will get stuck very soon. Try out yourself. Let u to be the other function, x squared or 3x squared, doesn't matter. The constant 3 doesn't play a part there. Doesn't change anything. So let u to be x squared. Can you follow the method and see whether it works? It won't. Very soon, the next step, you will find that you get stuck. So if you happen to choose the wrong substitution, you get stuck. Change it. Substitute another function. Yeah? All right? But if you follow this rule most of the time, you will get it correct. You follow this hint, all right? This clue. After that, then of course we got to change dx to become du, right? And as I said, I use this one. Du is du dx times dx. So from dx, you can change to du. And then all the original terms, all the variable x, the original variable x in the original integral, you change them to become x. That one can be done quite easily because you know the substitution function. U in terms of x, you already know, right? So you can do that, replace all the terms, all the x terms to become terms containing u, all right? Then you just carry out the integration. After that, you can integrate it, all right? Carry out the integration, and then your answer will be in terms of u. Of course, ultimately, we don't want u, right? So just change it back. Since you know u in terms of x, then you can change the function of u to become function of x. That will represent the final answer. So that's what you do in substitution. And let's look at few more examples. Few more, right? I think that there are quite a lot number of work examples here. All right, integrate or x cosine x squared dx. This cosine x squared is in fact something like that. It's not cosine x times cosine x. It's not. If it is cosine x times cosine x, it would be written as cosine square x. This one is cosine x squared, so there's a bracket here. But it's understood. We don't have to put the bracket, all right? Okay, so if you look at this thing, you differentiate x squared, you get x. You differentiate x, you don't get x squared. This follow this rule, right? You differentiate an inner expression, you get another function contained in the integrand. That indicate this is likely to be the choice for the new variable. So for this case, since differentiation of x squared is x, so we let u to be x squared, right? So we let u to be x squared. So this part is the most difficult part. You need to have some experience before you can appreciate and make the correct choice. Yeah? All right, so once we've done that, then of course we are going to change dx to du. How do we do that? Remember, du is what? Du is du dx times dx, right? So this du is always du dx times dx. For this case, du dx is what? U equal to x squared. Du dx is 2x. So this is 2x dx here. Right? So du, we can put du in terms of dx. And therefore, x dx is half du. Why we do that? Because in the original integrand, you see we have x dx, x times dx. So this one and this one together, we can change it to half du. Okay? So half, so the original integral here. So x dx now become half du, and the constant half can be brought outside the integration. Right? Okay? And then what about cosine x squared? Cosine x squared now become cosine u. You see in this new integral, there is no more x inside. Everything changed to u. And this integral can be done easily. The original one, no. How do you integrate this? Well, you got to go through this substitution. You can't integrate the original integral directly, this one. You can't integrate directly, yeah? Going through the substitution, we change it to something that can be done quite easily. Integrate cosine u, you just get sine u. So the answer is half is still there. Integration of cosine, you get sine u, right? And then don't forget the integration constant. And finally, change everything back to x. Since u equal to x squared, so quickly replace this u by x squared, and we get the final answer like this. So substitution. We are going to have a few more examples like that. The next one is this. How do we integrate this? 3 tangent x plus 4 to the power 5 times secant square x dx. So if you want to use substitution, observe the function inside. Inside, we have secant, we have tangent. Then think of this tangent or secant, differentiate what to get what. So you see that differentiation of tangent, according to differentiation, you get secant squared. So differentiate this tangent x inside this function, you get the other function of x in the integrand. Therefore, we let this u to be tangent x, and to make it better, we let this to be 3 tangent x plus 4, this one. So that when we differentiate, we get secant square. We get this part. All right? Okay? So we add 4, doesn't really matter, because when you differentiate, the 4 will be gone. Differentiate a constant becomes 0. So this tells you we got to let u to be 3 tangent x plus 4, because when you differentiate this, you get 3 secant square x dx. The constant 3, it doesn't really matter. What matters is you get secant square x, which is the other function appearing in the integrand, telling you that this substitution should be okay, right? In fact, it is okay. So once you decide on the substitution, then the rest will be straightforward, just like the last example. So work out du. Du is du dx times dx, right? So this is du. This part is du dx, right? Because du dx is 3 times secant square x. That's all, right? You differentiate this one, du dx is 3 times differentiation of tangent, which is secant square x. Differentiation of 4, you get nothing. You get 0. So you get this, right? So this is du dx, and then times dx. So now substitute. Substitute. The original integral is this one. After substitution, 3 tan x plus 4 become u. So this whole thing becomes u. So this is u, right? So the whole lot is u to the power 5, right? And this part we can multiply inside by 3 and then divide by 3 and then divide by 3, that 1/3 we can bring outside because it's a constant, all right? So what left inside is 3. So you may ask, hey, why is there a 3? Well, because du got a 3 there. So we artificially add a 3 there and then we divide by 3. Okay? So this 3 secant square x dx according to here is du. So everything changed to u, right? So this becomes something very simple. 1/3 u, the integral of u to the power 5 with respect to u. And using a simple power rule, become u to the power 6 over 6. And finally, u is 3 tan x plus 4. Put it back. So this becomes 3 tan x plus 4. Okay, start with the answer. Another example. Sine square root x over square root x. We want to integrate this, okay? So we must observe what we differentiate can become another function appearing in the integrand. You have square root x, you have 1 over square root x, right? This is square root x. This one is 1 over square root x. Which one we differentiate to obtain the other one? If you cannot see, then you try both. It's not difficult to try both, right? But in fact, the one to use is this one, square root x. Because when you differentiate square root x, you get 1 over square root x, isn't it? According to the power rule, which is written here. So if we let u to be square root x, which is x to the power half, you differentiate x to the power half, you get x to the power minus a half. Of course, you get a constant there. And this x to the minus a half is exactly the other function inside the integral, which is 1 over x, 1 over square root x, right? So this is what you do in substitution. Yeah? So this one, when you differentiate, you get half like that. 1 over 2 root x, isn't it? And this is exactly, the half doesn't really matter, it's a constant. What matters is you get 1 over square root x, which is the other part inside the integrand. So telling you that, oh, maybe we should let this to be u. So take this to be u, right? Here. Then du, according to the expression, du is du dx times dx, right? So du dx is half u times 1 over root x, this one, yeah, times dx. Okay? All right, then substitute. So the original integral, without substitution, we don't know what to do with that, with this, you know. And now, sine square root x, so this becomes u. All right, this one becomes u, no more square root x. And the whole thing here, this one, we divide by 2, outside we have a factor of 2, right? This 2 and this 2 cancel out, so it's same as the original one, 1 over root x, right? But we put a half there, so that this is now, together with dx, it now become du. So this whole thing becomes 2 times of the integral of psi u du, something very simple. The result is minus 2 cos u plus an integration constant. And put back u in terms of x, u is square root of x, we get the final answer. Okay, another example using substitution. Okay, this is another one. All right, so the numerator, denominator, right? 2 things, okay? Numerator, denominator. So there are 2 functions, isn't it? So, but this one is quite easy because you can see that if you differentiate the denominator, x cubed plus 5, you get 3x squared. We have the term x squared in the numerator, isn't it? So for the same reason, so we let this to be u. So let x cubed plus 5 to be u. And repeat the same procedure. So du is du dx. Take that. Du dx is 3x squared. So now here we have 3x squared here, and the whole thing multiplied to dx. Now substitute. This 1 over x cubed plus 5, or this x cubed plus 5, now become u. And this, we multiply 3 and divide by 3, so as to make this become 3x squared dx, which is du. Yeah, so this part is du. And this become 1/3 the integral of 1 over u, which give you log, right? Log the absolute of u. And put back u in terms of x, we get a final answer. So another example. So you will have to look at the integrand carefully and make the correct choice of what should u be. All right? Okay, this one. So integration of tangent x, okay? Tangent x, one function, one function, how to substitute? Well, we can change tangent x to become sine x over x so that we have 2 functions, right? And you can observe that in this case, cosine x, we can let cosine x to be u, because if cosine x is u, then du will contain sine x. Of course, d cosine x, you get minus sine x, but the minus is a constant. Minus 1 is a constant. It doesn't bother us. So when you differentiate cosine, you get sine. So we can let u to be cosine x. For the same reason, you can instead let u to be sine x. It still works. Your final answer will be the same. If you do so, then you differentiate sine x, you get cosine x, isn't it? So I think either way is fine. But in this case, we let cosine x to be u, and therefore, du will be, let cosine x to be u, so du will be du dx, remember this, times dx, right? And du dx is minus sine x, this one. This is du dx. Okay? Times dx, so the whole thing is du actually. All right? So that one, you change it, become 1 over u times the integral of 1 over u with respect to u. And this one, you get log function, log the absolute of u. And since u is cosine x, so we get our answer in terms of x. Okay? So this is yet another example for it. Okay, another one. This one. Okay, integration of this. The square of arctangent over 1 plus x squared. So now, to look for it, then you can see when you differentiate arctangent, you get 1 over 1 plus x squared, which is inside the integrand. Therefore, we let u to be arctangent of x. All right? So when you take du, when you differentiate u, then you get du dx, which is this part, times dx. So we are repeating the same procedure. All right? So the original integral now become this one. Arctan square, you get u square, right? And the other part now become du, so become something very simple, just the integration of u square. You get 1/3 u cubed plus constant c. And put back u equal to arctangent of x, so this is the answer. So we are doing the same thing quite a number of times, isn't it? Okay, what about this one? This one. Integration of x square root of 2 minus x. This is slightly different from the other example. In there, okay, you have a lot of, you have functions inside, you have x, you have 2 minus x, differentiation of one equal to the other. Well, differentiate x, of course you get x, right? Differentiate this one x, you get an x, but you don't get square root anyway. But it doesn't really matter whether we get square root. Differentiate this one, you get x. Differentiate 2 minus x, you also get x, right? So this way, we don't know which one is which, because you differentiate one, you get the other one, isn't it? So sometimes, if you don't know, there are only two choices. You just try out one by one. For this case, let's try u equal to 2 minus x. All right? If you try the other one, it won't work. Okay? It won't work. So let's try u equal to 2 minus 1, and therefore, we change everything to, so du, okay. Same as before, so du is what? Du dx times dx. Du dx is minus 1, right? Because of that. Du dx is minus 1, so minus dx. All right? Therefore, the original integral, we put a minus 1 there, and outside we have minus 1. All right? Minus 1 times minus 1 give you 1. So this one is actually, these two actually become 1, right? But the reason why we put a minus 1 is because we want to form minus dx so that it becomes du. So this whole thing is du. Yeah, du here. All right? So what happened to the integrand then? So x is now 2 minus u, right? This x, you've got to change everything to u, right? So x is 2 minus u, and this become square root of u. Square root of u. Okay? So now, the whole integral is now 2 minus u, this one. This becomes square root u, this becomes du. So how do we do that? Now we can multiply them, expand this. The original integral we can't do anything. If you look at this integral, what can we do? We can't do anything, right? But if you look at the new integrand, this one, to integrate this, we simply expand this into two terms. The first term is 2 times square root of u, this one. Second term is u times square root u. You get u to the power 3 upon 2. We can expand. But this one with the square root 2 minus x inside is 2 minus x. This caused the problem, isn't it? Now this 2 minus x become u, and therefore we can expand. So this one worked in a slightly different manner compared to the previous example. But it's still substitution. Yeah? It's still the same, using the substitution. The difference is that now we can expand. Originally we can't. So expand, you get this one, then it will be straightforward. Just integrate the terms separately. We get these two, and add a constant c there. So this is the answer in terms of u. Finally, substitute u equal to 2 minus x back. You get the answer in terms of x, this part. So that one is, this is the final answer, this one. Okay? This thing here. All right, so this is what you do, what we have covered all these examples, 6.9, 6.8, and all these 6.7, quite a lot, right? Wow, quite a lot. 5 or 6 examples already. But all of them concern indefinite integral. We never have any limit of integration, right? Yeah, there's no limit of integration. At the end, we have a constant c there, right? This one as well. This one also. This one also, right? We have a constant c. This one also indefinite, indefinite, indefinite integral, indefinite integral, all of them, yeah? So what happened to definite integral? Well, we can still apply the same technique, substitution, okay? And then, of course, when I show you definite integral, at the end, we have to substitute the limit of integration into the so-called antiderivative, right? We're going to make use of the limit of integration and put them inside the so-called antiderivative to find the final answer. Now, if we have definite integral and we are using the method of substitution, we do the same thing. But there is one thing you have to be careful. Now, when we make substitution, the variable of integration, when we use substitution method, all right, what do? The variable of integration x is changed to u. This is the variable of integration, right? Of integration. This is the new one. It's also a variable of integration. Now remember, when you have definite integral, I was saying that when you integrate a function of x with respect to x from a to b, this limit of integration are referring to the variable of integration, isn't it? So when we change the variable of integration to u, therefore, the limit of integration will be changed accordingly. From value of x equal to a to value of x equal to b, you change it to something, become a function of u with respect to u, right? Using substitution, you have seen in the last few examples. But now this integration will no longer be a and b, wrong. This is something you must take note, because now you got to find the value of u correspond to the original upper and the lower limit. Okay, Don't use a and b after the substitution, because if you do so, it is wrong. Why? Because the limit of integration follow the variable of integration. These a and b are for value of x. They are not for the value of u. Okay. So I think with the understanding of this concept, now we can look at some example. This one. Integrate of this thing, all right? Now we apply the substitution method. You can see that if you differentiate x to the power 4, you get x to the power 3, isn't it? Constant doesn't matter, as I said, all right? So you differentiate x to the power 4, you get x to the power 3, which is this one. Therefore, you let u to be x to the power 4 plus 5. Yeah? So that's how you know what should be substituted. All right? Then follow the same method, substitution method. So du is du dx, which is 4x cubed, right? Du dx is 4x cubed, but you differentiate this one, right? And then this du dx times dx, okay? And so we substitute. The original integrand is this one. This is the original integrand. Now become this. Square root of x to the power 4 plus 5 here now becomes square root of u, because we let u to be x to the power 4, right? Plus 5. So this is square root of u. And then the other one, 4x cubed plus dx. We put a 4 there, and then we divide by 4. All right? 4 and 4. These two 4s cancel out actually. But we add a 4 there so that we form 4x cubed dx, which can be replaced, can be substituted by du. So the integration become square root u times du. Okay? Now take note, all these are the same as before what I shown you in the previous so many examples. Take note at the limit. Now the original one, this is from x equal to 1 to x equal to 2. Of course, we don't have to write down x equal 1, x equal 2, because it's understood whatever variable of integration you have here, then the limit of integration will follow this. So by default, this automatically means x from 1 to x to 2 equal to 2. Okay? All right? So these are the limit of x. Now, if we change the integral through the substitution, it becomes square root u times du. So the new variable of integration is now u instead of x. Therefore, this lower limit will no longer be the original one. This will no longer be the original one, right? So we have to find the corresponding limit of integration for the new variable. How do we do it? Well, we know what we substitute using this one. Okay? So this relates u and x. Therefore, when x equal to 1, use this relationship. You can find the corresponding value of u. So substitute x equal to 1 inside. X equal to 1, substitute inside. Your u value will be what? 1 to the power 4 plus 5. That is 6. So now your limit is this one, 6. Why? Because when x equal to 1, it will give you u equal to 6. Same thing for the upper limit, u equal to 2. Put inside. It will give you a value of u equal to 21 here. All right? U equal to 2, 2 to the power 4 plus 5, you get 21. So you have to make that conversion. Change the upper limit from the original variable to the new variable. All right? So this is u equal to 6 to u equal to 21. Don't use 1 and 2. Okay? And then the rest will be straightforward. So the integration of this will give you u to the power 3/2 divided by 3/2. I mean, this integration, all right, straightforward, using the power rule. And now substitute the limit of integrations, u from 6 to 21. Put inside, and then use your calculator. You can get the answer. Okay? So another example. So this one. T times e to the power minus t squared over 2. All right? Okay, very good. I think these are last slide, or last 2 slides. Last 2 slides. Okay, so we want to integrate this from t from 0 to 15, all right, t from 0 to 15. So again, using substitution. Now, if you look at that, you differentiate this minus t squared. You differentiate this t squared, the constant doesn't matter. You differentiate t squared, you get t. You in fact get 2t, as I said, constant, never mind. Yeah? You differentiate t squared, you get t. So let the whole thing here minus t squared over 2 to be our u. All right? Okay? So in other words, we let our u to be minus t squared over 2. What is this? U equal to minus t squared over 2 du? I think there's something wrong. Let's work out. All right? So in this case, du will be du dx. So we will no longer be du dx, du dt, right? Du dt times dt, because we have t instead of x, right? So du dt is minus t squared over 2 dt. Hey, do I make a mistake here? Okay, now what we are going to do is let this to be u, right? Let this to be u. So you can see that du dt. Okay, I think we can look at it this way. So same thing, we let u to be minus t squared over 2, as you can see here. So from here we differentiate, we get minus t, right? Therefore, du dt equal to minus t. All right? So du will become minus t dt. This is what we need. Okay? Du is minus t dt. Okay. So with that, we can now